Welcome everyone. Thank you for being here, and my heartfelt thanks to Professor Beata Randrianantoanina for being here, for agreeing to speak at our colloquium. Professor Beata Randrianantoanina did her master's from Warsaw University and her PhD from University of Missouri, Columbia, under the supervision of the great Professor Nigel Kelton. Her research interest is geometry of Banach spaces. She is a full professor at Miami University, Oxford, Ohio, and she has authored numerous papers, articles, and she's given seminars all over the world, and she is recipient of numerous prestigious grants. So without further ado, I pass the baton to Professor Randrianantoanina.
Thank you very much, and thank you very much for your kind invitation to speak here. I would like to ask everyone to mute themselves, please, because I mean, unless of course somebody wants to ask the question, then please unmute yourself and ask the question, because. Or otherwise, please put it in the chat and I will answer it at the end of the talk, or possibly other people can answer during the talk. I do not see the chat during the talk, so if there is a question on the chat during the talk that needs immediate attention, then please unmute yourself and tell me about it. So I want to speak about a very old problem, the Banach-Mazur rotation problem. So let me start from this definition of rotation. This is a traditional name, not so much used anymore, but used in this problem. I will use rotation to simply mean a surjective isometry U on a Banach space such that U of 0 is 0. So this is a classical result of Mazur and Ulam from 1932, from the very beginning of the theory of Banach spaces, that every rotation is linear. So, meaning for us, rotation means surjective linear isometry U on a Banach space. Now what happened to my... It is also well known that if H is a Hilbert space, then for every 2 points in the sphere of the space, oops, I'm sorry. Let me do this. For every rotation in the sphere of the space, for every 2 points in the sphere of the space over here, there exists a surjective linear isometry that takes 1 point to the next. So this is standard fact, and this fact gives this name transitive to the space. We say that a space which has this property that is described over here is called transitive, and this is what our problem is about. Our question is it true that every transitive space, and I need to adjust something here, I apologize. I think I wanted to do this, yes. Yes, then you can see the whole slide. I'm sorry about this. So, is every transitive Banach space isometric to a Hilbert space? So this question was posed already in the book by Banach. And it is, and what I want to talk about today is the current state on research on this problem. The problem in full generality is still open. So there are many questions at the end of the talk that I will present. Some of them look very simple, some of them don't. There is lots of open questions in this area. So I remind here this problem one more time. So the first work on it was done already in 1938. Mazur answered and said that it is yes, in case it is a finite dimensional space. Well, so However, in 1962, and as far as I know, that was the next time that this question was answered, was studied, and some progress was made. The answer is no in general. It's no in the case when the space is non-separable. So the way they did it is they did the ultra products of LP spaces. It is known, so I will maybe mention it in a moment when I introduce the definitions introduced by Pełczyński and Rolewicz. So let me first say what is the modern Banach-Mazur rotation problem, which is open. So the spaces that Pełczyński and Rolewicz discovered are non-separable. So in the case when they are separable and infinite dimensional, does it mean that every separable infinite dimensional transitive Banach space is isometric to a Hilbert space? And this problem can be split into two parts. So when we're asking here for it to be isometric, well, let's make it weaker. Will it be isomorphic at least to a Hilbert space? We don't know the answer to this question either. And second part, the isometric part, imagine that the space already is a Hilbert space. And now we are trying to renorm it. And we renorm Hilbert space in such a way that it is transitive. Does it mean that we obtained the original norm, the Euclidean norm? Or can we produce a second different norm on Hilbert space, which is also transitive? So I will talk more about these questions as we go through. So the study was started by Pełczyński and Rolewicz, and they introduced the notions which I will be using. So notions and notations. So the first notation is very natural. This will be our notation for the isometry group, the group of all isometries, surjective isometries on X. The S of X is the standard notation for sphere and the ball, the unit sphere and the unit ball. And the orbit is when you take a fixed element X in the sphere, I will only be doing it in the sphere, then you just look at all the possible images, which is always a subset of the sphere. And that's called the orbit. So definition, the norm is transitive if for all X, every other point of the sphere can be obtained as an image of some isometry, meaning the orbit is everything. And then they introduced a new definition called almost transitive, which means that the orbit is norm dense, meaning when you take X, if you take X in the sphere and you take, so for every X in the sphere and for every Y in the sphere, and for every epsilon, which is positive, there exists T, which is an isometry of X, such that T of X maybe is not Y exactly, but is epsilon close to Y in the sense of the norm, right? That's what it means to be almost transitive. All right, so I don't know if those definitions are familiar to everybody. So the norm, so remember here the beginning of this sentence, the norm is called maximal. Maybe I should use a different color than blue. If the isometry group of this norm that we are starting from, is called maximal, in a standard meaning of the word maximal. If that isometry group was contained in the isometry group of a different equivalent norm, then they would be equal, meaning you cannot you cannot increase this group strictly increase this group. I do not claim that this other norm is the same norm as the original that we are looking at. I'm just saying the isometries are the same. This is not, it's conceivable that you have different norms which have the same isometry group. Okay, so this problem has been studied by many mathematicians. It's impossible to mention them all here in this talk, but what is something that so typically, I mean, currently, we still don't have the final result. What we want is we want to have the statement that would say X is, and here I put this blank, because maybe I want to say almost transitive. They introduced other notions of transitive, which I don't have time to talk about now, but if it is in some sense transitive, and then unfortunately current results require this extra condition here, plus we have some property of the norm or of the isometry group, and then we conclude X is isometric. If we would prefer to have a statement without any additions, but currently we don't have such statements. So as I said, such statements, there is a significant literature, and there are many surveys. I won't be able to mention all the results. It's too many for 1 hour talk. So the plan for our talk is to talk about almost transitive spaces. We will mention some examples. We will mention examples that have multiple renormings. And we will outline some of the methods of proofs. And then we will talk about maximal norms. And then, if time permits, I'm going a little bit slower than I was hoping, we will do multidimensional Banach-Masood problem. And we will have open problems. Time will definitely permit for open problems. So here is the reminder of what I mean by almost transitive. And here are some examples of separable almost transitive spaces. So these examples are standard spaces. The most familiar space LP on 0, 1 is almost transitive in its standard regular norm that we all know. So this is what I mentioned, that Pełczyński and Rolewicz, I mean, I think that possibly Banach knew it, I am not entirely certain. The isometries of LP were described by Lamperti in 58. Pełczyński and Rolewicz notice that if you take ultra power of the LP spaces, then that epsilon can become 0, and the ultra power of LP will be transitive, not almost transitive. But of course, ultra power of LP, and this is for every p in this range between 1 and infinity, the ultra power of LP is not a separable space, but it is transitive, and it is not isomorphic to a Hilbert space. So that was the first discovery about it. So then Graham, Jamison, and Kaminska in 94 proved that if you take here any almost transitive space, and if you take a space, a Bochner space of vector-valued functions LP01 with the range in X, then that remains almost transitive. So, for example, LP of LQ for different P's and Q's will be transitive. Lusky in 79 proved a very striking and strange result. Proved that every separable space is isometric to a one-complemented subspace of some separable almost transitive spaces, which means that those spaces should be plentiful, right? And in particular, there has to exist spaces without a basis, without an approximation property, because such spaces have to be one complemented in an almost transitive space. This is very surprising. And something that I personally found very surprising is that the space of continuous functions, so like the standard norm on continuous functions on 0, 1 is the sup norm, and that norm, as is well known, is actually not almost transitive. However, and as I said, I find this result very surprising, Cabello-Sanchez found a different equivalent norm, which is almost transitive. I mean, this is very surprising. And at this point, one wonders, well, is everything almost transitive? But before I get there, let me talk about even a stronger thing over here. I want to talk about a notion of different almost transitive renormings. So first of all, maybe let me do this. So I will introduce this name conjugate, because, like, you know, in some way one could kind of cheat, like one could just take a bounded linear automorphism meaning it's a surjective linear mapping of X onto X, and just move my X somewhere and say, okay, so my new norm is just the original norm of the image, right? Here I kind of use the norms maybe in a non-standard way, right? So that is kind of cheating. It's really the same norm as the original, right? So if two norms satisfy this condition, I will call them conjugate. So they are technically different norms, but not really. So it turns out, so another way to say that they are conjugate is to say, well, we could say, because we have isometry groups and and there is a algebra meaning of the word conjugate, which is this one. So is this and this the same condition? Well, in general, no, because you could have an isometry group which is trivial. There are no isometries at all beside identity and minus identity. And those norms, and they don't have to satisfy this strong condition, but they, of course, would be the same group, not just, oops, what did I do? Okay, so what is an important observation here that, which I don't know why it's not written. Okay, oh, I did write it, I just wasn't thinking about it. So if the two spaces, if the two norms are almost transitive to begin with, then those two notions are the same notion, right? I said that if this isometry group was trivial, this wouldn't necessarily be the case. But of course, if the group is the space is almost transitive, the isometry group has to be large. So in that case, if both of these norms are almost transitive, then this condition and this condition is the same condition. And this is what I want to talk about here. I want to talk about spaces LP, which we know are almost transitive. And I am saying that this space LP has at least a countably many non-conjugate, almost transitive norms. So this is maybe surprising, but it's not really. I don't believe anybody said it. We mentioned it with Cabello-Sanchez and Ferenczi in our most recent survey, but it really is something that comes straight from the literature. So it is well known that if we use Hn, which are n-dimensional Banach spaces, n-dimensional Hilbert spaces, then LP of Hn is isomorphic to LP. And by the result of Graham, Jamison, and Kaminska, since Hn is transitive, LP of Hn is almost transitive. And there is a result of Camburn and Graham, also classical, that those two spaces are isometric if and only if n and m are the same dimension. And since we are requiring this condition, we are, for the norms to be conjugate, this will happen even only if n equals m by the result of Camburn and Graham. So we have, kind of for free, we have countably many non-conjugate, almost transitive norms on LP, on our first example. On C01, this follows from a result of Ezipuru and, I don't pronounce those names correctly, I'm sorry, Ezipuru and the second name escapes me, the same thing. I don't want to go into this. And then there is a Pełczyński space with a universal basis, which has a continuum of mutually non-conjugate, almost transitive norms. So I am kind of behind, so maybe I am not going to go through the proof of it. This is what is the rest of this slide. So first there is a reminder of what this Pełczyński space is. So this is standard. I guess one could just, if you don't remember what it is, let's just say there exists a space which has a continuum of mutually non-conjugate, almost transitive norms. Then there is a trick with ultrapowers, right? If we take ultrapowers, we obtain transitive norms. So we have non-separable, so there exist non-separable Banach spaces which have continuum on pairwise non-conjugate transitive norms. And the same and also in LP, right? So this kind of makes sense. This isometric part of the Banach-Mazel problem, the question is, if we have a Hilbert space, is it possible that it also has some pairwise non-conjugate transitive norms? Many? Just two. That's the question. Does it have two different ones? Or does it permit, if you don't want transitive, can you produce a non-conjugate almost transitive norm? I mean, on every other space that is almost transitive, that we know is almost transitive, we know how to produce additional norms with that same property. So can we do it on a Hilbert space? This is open. And here is a natural question that actually I already said. All these natural spaces, and because of the result of Lusky, it really makes sense to ask, well, does every space admit an almost transitive norm? Well, the answer to this question is no. Again, Cabello-Sanchez in '98 showed that if X is reflexive and almost transitive, then it's going to be super reflexive. But super reflexive, of course, is an isomorphic property. So, so if a space is reflexive but not super reflexive, that means you cannot renorm it to be almost transitive. So we of course know that such spaces exist. So C0, L1, here are those modern spaces, Chilson space, Schrumbrecht space, many more space, every space which is reflexive but not super reflexive. So the question, the natural question that comes, actually this question was posed even before Cabello-Sanchez proved this result. They had the insight that said, well, super reflexive. Is it true that every super reflexive admits an equivalent almost transitive norm? Well, it was answered 20 years later. No, 10 years. 20 years later. It was answered 20 years later by Ferenczi and Rosendahl, who said, no, it is not so. There exist complex Banach spaces, which are separable and superreflexive, and they do not have an equivalent almost transitive norm. And the examples that they used were spaces which are HI, hereditarily indecomposable, and in particular don't have a shoulder basis. And I cannot go into the definitions of these things. I feel behind. So then the question, I'm not sure exactly why my slide is not shown. The question is, does there exist, is this too small or is this big enough? Okay, this is big enough. Does there exist a real, right? Because they proved it for complex spaces. So the question, they remained open. Well, can you have a space, when I mean, say real, I mean over the real scalars. This question was answered by myself and Dilworth in 2015. We found the long list of classes of Banach spaces which do not admit an equivalent almost transitive renorming. So the list is long, and it starts from the most classical sequence spaces LP with the standard norm. They cannot be renormed to be almost transitive. I will try to explain why. None of the subspaces can be renormed to be almost transitive. And none of the subspaces of LP sum of finite dimensional normed spaces can be renormed either, which in particular means that subspaces of quotient spaces of LP cannot be renormed to be almost transitive. Subspaces of capital LP, right? We know that capital LP itself is almost transitive, but subspaces of capital P for P which is bigger than 2 that do not contain a subspace isomorphic to L2. Right, so in particular, LP itself is fine. It can be, I mean, does have an almost transitive norm. Subspaces of any Orlich sequence space which does not contain a subspace isomorphic to L2. If it does, then we don't know if it can be renormed to be almost transitive. Subspaces of asymptotic LP spaces, and here is a quick reminder of what asymptotic means. I will maybe skip this definition right now. So what is the proof of those things? So the key lemma, method of proof. The key lemma is the following. We have here, I am thinking of it like existence of a circle. So we have that if you have a Banach space X, which has a Schauder basis, and if X has some subspace, which is almost transitive, and then for every delta and every y in the sphere of y, so here is 0, which is in the space, here is y0, and we say that there will exist a second element in y, which in the sphere of y, which is almost disjoint with y0, right? When I say almost disjoint, I mean in the sense of this basis, which is such that the two of them together, so this will be the y0, I am drawing it like this, and I am saying that when I draw this circle, it looks like the standard two-dimensional L2 circle. I mean, up to delta. So trust me that this is my best approximation of the standard Euclidean circle. So we say this happens as long as X has a infinite dimensional almost transitive subspace. So the proof of this result is actually very simple and quick. It relies on the classical Dvoretzky theorem. That's the big gun in this proof, but it's very classical by now. And almost transitivity and compactness. Now, compactness is needed to say that it's going to be this almost disjoint. from the original one. So once we have this theorem, we can conclude that, well, why don't we do induction and do it over and over and over again, right? I mean, let me go back there. Here, I am saying that those two vectors, whatever scalars you put on them, it behaves like the L2 norm, the standard L2 norm. So here is an expression for the standard L2 norm. However, we cannot do it for arbitrary scalars. What we can do is that once you choose a sequence, let me maybe, show this warning right away. Once we choose a sequence, for that sequence, see, there exists this over here. After we selected the sequence, you can, depending on the sequence, you can choose the sequence AK of numbers. You can choose the sequence, which is a normalized block basis in X, so that this happens. So here is the L2 norm of my pre-selected sequence, and here is the norm in the space. So this block basis does depend on which sequence of scalars we choose. But for that sequence of scalars, the formula for this norm is L2, right? With some, small perturbation, which can be as small as we want. So here is maybe the one proof that I don't want to skip. I will show that no subspace of the classical LP can admit an equivalent almost transitive renorming, right? So this follows from this lemma that we just saw. So first of all, imagine we have a subspace and which has an equivalent. This is my abbreviation for almost transitive. And let's extend this norm to the whole space LP, which is again classical that this can be done. And apply this previous corollary with the fixed epsilon and with this constant sequence. I need to choose a sequence, so let me choose this one. So there will exist some disjointly, this is the key element of this whole proof, disjointly supported sequence, right? I mean, over there I said block basis, meaning I want my supports to be one after another. But I don't even, so in particular, they are disjoint. So since they are disjoint, they behave like the L2 norm of this constant sequence. The L2 norm of this constant sequence is this much, and epsilon is 1/2, so we obtain these inequalities. Right. However, since I have a disjointly supported sequence, of every block basis, we know what it does in the standard norm of LP. It's isometric to the standard basis of LP, meaning in the standard norm, the block basis will have this norm. Now, our norm is not the standard norm. However, it is equivalent to the standard norm with some constant C, which is fixed at the very beginning, right? We don't know what it is, but it is finite. So now, that means that I have those inequalities for this new norm, because we know that the standard norm would give me precisely this norm, right? So let me uncover what was written there. Well, this is a contradiction if M is large enough, right? I mean, because once I fix this sequence, for every M, I can produce this. Well, that's contradiction. That's the end of the proof. This is kind of surprising how simple it is. Maybe this is, I hear that there are many students here, and not only students, right? I am no longer the student. I am still very interested in this problem. It seems like maybe there is still some questions here that are accessible. In particular, what I want to maybe mention right away, right now, we still don't know if I take the space LP of LQ, right, the vector value, we don't know, does this admit a finite, an almost transitive norm or not? We don't know it. And if I take LP plus LQ, we still don't know it. There are still very many very open questions. Okay, maximal norm. So this is a reminder of the definition that I said. Well, it's the standard meaning of the word maximal for the isometry groups. So what I want to say over here very briefly is that when you have an equivalent norm, then you have the isometry group, and that isometry group is bounded, is a bounded subgroup. What does it mean, bounded subgroup? Well, if I take, because this is a group of all bounded surjective isomorphisms of X, and if I have a subgroup, right, but here, of course, for every T which belongs to GL of X, it's the norm can be, you know, arbitrarily large. There is no restriction. But when I say bounded subgroup, I mean that for every T, then no in this subgroup G, this norm, whatever original norm here was taken, this was X with some original norm, the norm of this T in the subgroup will be smaller or equal than the C, which is fixed for the group, right? That's what would mean that it is bounded subgroup. So the thing is that if that subgroup, if this is a group of isometries for some different norm, then T squared is also an isometry in this norm, meaning its original norm is still smaller than the same C, because that norm is C equivalent to the original norm. So if I take any type of compositions of these isometries, they remain isometries in the new norm, meaning they have the same bound by the same C, meaning they are a bounded subgroup. So on the other hand, if I do have a bounded subgroup, then I can define a new norm depending on that group G simply by this condition, right? It's always bounded, so let's produce a supremum. So this is, it's easy to check, this is a norm, and G clearly will be, every element of G clearly will be an isometry on this norm, meaning it will be a subgroup of the isometry groups. And this will be a subgroup, a bounded subgroup. So when I am talking about a maximal renorming, a maximal norm, I am talking about a maximal bounded subgroup of the group G, GL of X, of the group GL. Right. So. And so this is kind of a modern connection with the group theory, and there are some important theorems that are there. So, the questions, we want to study maximal isometry groups. So Auerbach, in a series of 3 papers in early 30s, proved that if you take the scalar product on X, as long as X is finite dimensional, that produces a maximal subgroup. And that also produces a transitive norm. So every finite dimensional space has an equivalent maximal norm, which is the transitive norm. And Rolevich proved that every almost transitive norm is maximal. I do not have time to go over this. I guess I didn't plan to really even go over this. I guess I just wanted to show this is a very easy and quick exercise. This is the entire proof. I'm not going to show it. So Rolevich also proved that every symmetric norm is maximal. For example, the standard norm on LP, the standard, I mean, we know many one-symmetric spaces. Sometimes they are called rearrangement invariant spaces, like Lorentz spaces, sequence spaces. Orlik spaces and many others. Right, so the question that Wood asked in 1982 is, does every Banach space have an equivalent maximal norm? Right, in view of the result of Rolevich that every almost transitive and every transitive norm is maximal, this is a weaker version of, much weaker version of the question that was asked, does every space have an almost transitive norm, right? So over there we know the answer is no, but here, well, does it have a maximal norm? So this question was again answered by Ferenczi and Rosendahl in 2013. The answer is no. In fact, that's how they answered that it cannot have an almost transitive renorming, because almost transitive renorming would be maximal. But they did it in the case of complex separable superreflexive spaces. And so those are the same examples as we mentioned earlier. Oops. And it was, the question was in the case of the real superreflexive spaces. So my results with Dilworth saying that LP doesn't have an almost transitive renorming, of course, do not answer the question of Wood. We do know that little LP has a maximal norm. I mean, the original norm is maximal because it is symmetric. All right, so how much time do I have? We started a few minutes after.
You have 17, about 20 minutes.
I have about 20 minutes. Oh, it's much better than I thought. Thank you. So, here, so as I said, the problem in LP, our results, my results with Dilworth in LP, which say that LP doesn't admit an almost equivalent renorming, an almost transitive equivalent renorming, of course, do not address, are not a counterexample for this problem of Wood, right? I mean, of course, little LP admits the standard norm is maximal, right? But Wood asked also a second question, kind of a stronger question. So is it true that not only that every Banach space has an equivalent maximal norm, right, which right now we don't know, we know it's not true for every space, but they asked, well, imagine that our Banach space has maximal norms, right? Such Banach spaces exist, for example, little LP. And then, so if we know that it does have maximal norms, does it mean that there exists a maximal norm which contains my norm, which contains the isometry group of my norm, right? That every bounded isometry, every bounded subgroup is contained in a certain maximal one, provided that we know that maximal subgroups exist. And the answer to this is no in the case of little LP. So little LP is a group, is a space where maximal bounded subgroups exist. So if I renorm LP in any way I wish, will it have to be contained, the isometry group, in one of those maximal groups? And the answer is no, strangely enough. And here is a picture of how to produce it. So this is like, just an illustration. But the idea is that what this is representing is I am representing LP as the LP sum. This is a very complicated K, so I equals 1 to infinity. LP sum of those things here, you see it's written L2, a Hilbert space of dimension K1. So here is L2 and here is dimension K sub I. Right, so I take such a space. So on the first coordinate, I put my L2 of some dimension. Here is a different dimension. Here is a different dimension. I go like that forever. And it is a standard fact that no matter how I pick those dimensions, as long as they are all finite, this space is always 4 isomorphic to the original LP space. Doesn't matter how I pick it. So if that is the renorming, so this is an equivalent renorming of LP. And now, again, it is well known that the isometries of it, if my dimensions are all different, the isometries have to be such that if I had those, I think of those things as fibers. Oops, I know I am motioning with my finger, which you don't see. You only see my cursor, right? So as I am, the isometries would allow a reshuffling of the coordinates of LP, but they would require the isometry of this fiber with this fiber. But here the dimensions are different. They are not isometric, meaning this reshuffling is not allowed. The only isometry that exists in this space is that within each fiber, I mean, the fiber is L2. There are many isometries in that fiber that I can introduce, right? Change this for something isometric, right? What is the norm in this space? The norm of such a xi element in this space, I said LP, I should have said X. Well, Y. This is my new renorming. Y is isomorphic to LP. That's what I meant. So when I said here this equal, I meant it in an isomorphic sense, not isometric. This Y is 4 isomorphic to the original LP. And if I have this element here like this in this Y, what I mean by it, and this is equal, is I mean that I take the norm of each xi, a 2 norm, right? Each xi belongs to this fiber, which is a Hilbert space, and then I apply a p norm to it, which is take this 2 norm. Everybody knows the formula for the p norm, right? So this is an LP sum, right? This is what I mean by this symbol LP sum of those Hilbert spaces. So of course, if I change xi, if ti is an isometry of this L2ki, then ti of xi, the L2 norm, will be the same as the original norm, right? Since it is an isometry of that fiber. So it will remain an isometry of the whole thing. And I am saying those are the only isometries if I pick those dimensions to be different. So this is the isometry group of this space. Well, is it maximal? Well, no, because if I now combine, say, the first 2 fibers and make 1 fiber out of it, which will have dimension K1 plus K2, right? I combine it and make it into L2. That, of course, will increase the group of isometries. I mean, L2 of finite dimension has a larger group of isometries. As long as this K2 is still different, smaller than K3, strictly smaller, then the new space I obtain is the same as the one a moment ago, and the isometry group is strictly larger. So if I am careful in choosing those dimensions in such a way that whenever I combine the original dimensions, right? Because of course here my next idea will be, all right, so I combined these two, and then I will combine the first two again, and so on, inductively. Every time I get a larger group of isometries, provided that those dimensions were chosen carefully so that they never match. They are always smaller than the next, which of course can be done very easily. So you can produce, and I am saying even you can do it in continuum ways, choose those dimensions to satisfy this condition. This is very standard. So even the space LP, the most familiar space, doesn't satisfy this fact that the isometry group is always contained in some maximal one. Here is a sequence of bounded subgroups which does not have a maximal one. This was kind of surprising to us. All right. Well, so again, spaces with multiple maximal renormings. Let me show you the picture. So again, we say that the space LP, the standard LP, again, admits a continuum of equivalent renormings, which are all maximal, meaning we have a big bunch of maximal groups, not just the original renorming, but this renorming. So like here, the difference is, it's a very similar example as a moment ago. The difference is that this time I want all dimensions to be identical. So then the isometries are such that, of course, within each fiber, one can apply an isometry over two, which there are multiple, but also all fibers are identical. So I can move one fiber to a different position. I mean, the LP sum is, LP norm is symmetric. We, of course, can apply here any permutation we want, and we have a big bunch of isometries. And that isometry is maximal. This is not very difficult to check. And then, so like here, well, so this is actually what this is checking, that for every K, this is maximal. So like one would say, well, what if I combine the fibers? What if I, so I hear those colors are indicating that I combined fiber 1 and 2, and 3 and 4, and one would think, well, didn't I increase the number of isometries here? Right here, I had isometry, the arbitrary rotation in this Hilbert space and arbitrary rotation in this Hilbert space. This is a bigger Hilbert space. Is that a strictly bigger norm? Well, the answer is no, because before I could move fiber 2 to 4 and fiber 1 to 6. If that's what I wanted, that is one of the permutations that allowed. Now, this fiber can be moved somewhere. For example, it can be moved to this fiber, which combines 3 and 4, but that would force the first fiber to go here. It cannot go to this one. Right, this is not allowed anymore. It has to stay within this fiber. So that means that this isometry here is not, this isometry group of this is not a subgroup of the isometry group of that. This is actually a maximal subgroup. And all right, so we can have this very rich behavior that we have continuum many maximal subgroups, but we also have continuum many groups which are not contained in either of these maximal subgroups. Sorry. Okay, so if time permits, I'm not sure that it really does permit. So let me just show this slide. I have 5 minutes. So maybe I have, let me show this entire slide. And just say very briefly what I mean over here. So what I mean, I will introduce this difficult to pronounce word, which I will call simply UH, ultra homogeneous, right? I am trying to be ultra is the strongest word I can think, right? So what we have is that every finite dimensional subspace and every isometry is extends to the global isometry. So that means that if I have E and I have some isometry U that goes into X, which is linear and isometry, then I will have, there exists capital U in the isometry group such that U restricted to E is precisely this isometry. It also means that if I had two different isometries, let's call them F, that isometrically embeds into X, and say I embed E isometrically into G, then there exists an isometry T of the whole space such that F equals G composed with T. Right. So, which means that this canonical action is transitive. So what it means really is that if I have two different, right, so this goes, I said, into X, but it goes into, you know, F of E, and this one goes to G of E. So I am saying, when we said transitive, we meant that for every single point, we can map it to wherever else we want on the sphere. Now I am saying, for every finite dimensional space, we still imagine that this is possible. So, meaning we can find an isometry which maps this finite dimensional space, which we know is isometric to this one. Can you find an isometry T which maps the first copy to the second copy, which is much more than transitivity. So that's why we are using these strong words over here. It's ultra homogeneous. And here is a multidimensional Mazur problem. The surprising part is it's also open. Even with this strong assumption for every finite dimension, imagine we can do it. Does this imply the space is isometric or isomorphic to Hilbert space? It's open. Right, so I guess you will have the slides, so you will see the rest of it more carefully. I don't want to talk, well, I want to, but I don't have time. I don't want to skip the open problems. So most of the problems I already mentioned. Does Hilbert space have a second renorming, which is transitive or almost transitive? Does LP, the standard LP, admit a transitive renorming? This is also unknown. Does there exist any symmetric space, or sometimes they are called rearrangement invariant, other than L2, of course, which admits an almost transitive renorming? So we know that little LP doesn't, but for Orlich spaces, if they contain a Hilbert space, then we don't know. And suppose that every subspace of some Banach space admits an equivalent almost or transitive or almost transitive renorming, right? We know this happens in Hilbert space. Every subspace is also a Hilbert space. Does this condition imply that X has to be a Hilbert space? We know it's true in case when X is a subspace of capital LP for P bigger than 2. If every subspace admits an equivalent transitive renorming, or almost transitive renorming actually, then it has to be a Hilbert space in this special case. In general, we don't know. This is a question of Ferenczi and Rosendahl. Does there exist a separable real superreflexive Banach space which does not have an equivalent maximal norm? And then the question about this uniqueness. uniqueness of maximal bounded subgroup. Right? Little LPs have continuum many maximal subgroups. A similar example would work in every symmetric space. There are many spaces where this example that I described would work. Does there exist any Banach space at all which has a unique maximal subgroup? Is this true for Hilbert space, for example? We don't know. This is really that isometric part of the Banach-Mazur problem. If it is true for Hilbert space, would Hilbert space be the only space satisfying this condition? And then this is, the extension from that last part of the Woods question. Does there exist a separable Banach space such that every bounded subgroup is contained in some maximal bounded subgroup? Is this true for Hilbert space? Is Hilbert space the only one that would do that? So those are the open problems. They are very open. And thank you very much for your attention.
Yeah, thank you very much for the nice talk. Maybe Sudeshna can say something because he introduced the speaker.
Yes, thank you, Beata, for a wonderful, wonderful talk. Any questions, anyone? Any questions?
Yes, I have
Yeah.
This last property, this last property introduced, which is the ultra.
You mean the multidimensional one?
Ultra homogeneous.
Ultra homogeneous. Yes. Let me go back here. Yes, this is the slide. Yes.
So suppose that this finite dimensional subspace E, this has two distinct embeddings in X.
Yes.
That means, does that mean that that the images of these two under these different embeddings, they can be, there is a isometry in E in
yes.
X, which will take one image to the other one.
Yes, that's precisely what it means. That is exactly what it means. So that you embed E. So it really is precisely what you said. So you have this space, some finite space E. You embed it once, and you produce here. Let's call it F. No, F is not a good letter.
X. You mean X?
Well, the whole space is called X. So, yes. So let's say I shouldn't be hanging up on this. So you produce. I don't know why it's not working. Okay, so you embed E once, and you produce F, and you F1, and you embed it again, and you produce F2.
Yes.
F2. And those F2 are clearly isometric to each other, since they are both isometric to E. This condition precisely means there exists T, which is from X onto X.
Yes.
Such that T of F1 equals F2.
And is T, in any way this T can be related to a conjugation? Can it be called a conjugation, this T?
Well, it looks like conjugation because we have here this first embedding F1, and we have here this second embedding F2, right? And we said F1 got extended to some isometry T1, which when you restrict it to E, this is little f1. And then F2 similarly got extended to this T2, which when you restrict it, is the F2. So then what will be this isometry T? Well, this isometry T will be the the T inverse restricted to this image, right? It will be T1 inverse, right?
Yes.
We will apply
That
it
is
only on F1 and then T2. So yes, it does look like the conjugation. That
because you have a commutative square, I think, in this situation.
the commutative.
You have a commutative square of some sort. You have some commutative square when you in this situation. I mean, can you make a diagram?
You have a diagram, yes, which commutes. Yes, precisely. I should have drawn it on a diagram. It would be a lot clearer.
Yes,
Let me go back here a little bit so I have room to draw. Yes, that's precisely what it is. You have those isometries, and so you have this E, and you have this. You're absolutely right. This is that diagram that commutes. And then you have this.
Yes, exactly.
Yes, that's exactly what it is. Yes, absolutely.
But, I mean, there is a second question which is related to this one. That if you have a Banach space X, is it possible for the elements of X to generate isometries of X?
What do you mean by generate isometries?
For example, if you have a group, then if you take an element in the group, an element can, conjugating by the element, you can get an automorphism of the group.
Well, so I guess what you mean is this thing that I showed earlier about the connection. If I have a group, let me try to, maybe this is the better way to find it. If I go back to the, it's very small, I don't see it here. Yes, here. So if you have group, if you have a bounded subgroup of all automorphisms on X, you can define a new norm using this bounded subgroup by this formula, and that produces a new norm which is equivalent. Is that what you mean?
No, I'm sorry about this, but if we consider algebras, then we have we consider associative algebras. Then we have what is called the Skolem-Noether theorem, and this.
What? I'm sorry, I didn't hear. The Skolem.
So if you consider finite dimensional algebras.
Yes.
So I mean, there is a theorem which is called Skolem-Noether theorem. This applies.
I am afraid that I'm not familiar with this.
Okay,
so
but
it's going to be difficult for me to answer the question.
It is very similar in essence with this ultra-homogeneous space that you can get if you have two. So if you have two embeddings of a simple algebra, then these two images can be obtained by an automorphism of the bigger object.
Okay.
I mean, they can be mapped into each other.
I understand.
Yes. Well, so that automorphism is a conjugation, in fact. In the Skolem-Noether theorem, that automorphism which takes one image to the other image, that is that is a conjugation. Yes. So I was curious that in this case also, because this thing is quite, I mean, this is a similar, I mean.
Well, so how is it in this case? So in all honesty, in this case, the only example that we know of a space which is ultra-homogeneous is a Hilbert space. It is open whether or not that's the only example. I mean, let me rephrase it. This is the only example which is separable. There are non-separable spaces which are not isomorphic to Hilbert space, which are ultra-homogeneous. In particular, if you take the space LP, I didn't have time to show it. Maybe let me show that next slide, which I didn't have time. The last slide, which I didn't have time to show. So there are spaces which are Oh, I'm sorry. So we actually don't know any examples of, so here we introduce an approximately ultra-homogeneous, and we show that the no, I'm sorry, this is right. So what we have, it's not written on this slide, I forgot that I didn't write. If you take LP, P not equal to 4, 6, 8, and so on, not equal to any even integer, and then you take the ultra power of this LP, then that space, which is non-separable, is going to be ultra homogeneous. If you look for separable examples, we don't have any, so we don't really know how it works. So in LP, the way we prove that this thing is ultra homogeneous, in LP we understand, we use the so-called equimeasurability theorem to prove this, meaning when you have that isometry, the embedding into LP, there exists an extension of it, which is not exactly an isometry. That's why we use here this approximately an isometry. So even though the original thing is an isometry, the extension is an almost isometry, and then you have that diagram commuting. And those are really the only examples that we understand. We don't know if there are any other spaces, well, apart from Gurari space, where this holds. We know it doesn't hold in LP. For your question, in general, I don't know. It's a very good question.
But you know, the Skolem-Neukert theorem that I mentioned, that's the Skolem-Neukert theorem that I was mentioning.
Yes.
That says that, you know, you can always bring one of these images to the other images by means of a conjugation in the bigger.
I would be very interested in looking at that. I do think that this could be very useful, but at this point, my answer is I don't know. But it is a very interesting question and a very interesting connection. I would be grateful if you can email me the name of that theorem, and so I can, you know, learn more about it. And I would be very interested in that.
Sure. I will send you. Thank you.
Thank you.
Any other questions? Any other questions? If not, I'll just like to ask one question. So, Beata, all these properties that you introduced, like transitive and almost transitive, and as far as I remember, you mentioned that, for example, it is for finite LP sum, if all the spaces are transitive, then the finite LP sum is still transitive, right? Something like that?
Yes. Yes, that is the result of Graham, Jamison, and Kamiska. Not only finite LP sum, well, actually, I am sorry. So let's be careful over here. I don't mean to say what Jamison and Kamiska proved, that if you take LP of X, and X is almost transitive, then that Bochner space is also almost transitive. But not, including, but it's not going to be true for, I mean, we don't know if it is true for literal P sum.
Okay. So my question now is, can we say anything about, for example, X is almost transitive. Can we say anything about the space of bounded operators on X, or say tensor products?
I don't know of any results in that direction.
Okay, so that was my
But
question.
also, are those spaces going to be separable?
Yeah.
Because Mazur question, I mean, it would be interesting to know it also for that kind of examples. We are interested in non-separable examples also. And as I said, every time we have something, we point. So there exists, but I don't believe that's wrong. I don't believe it.
And for example, if we have a Hilbert space, can we say anything about the bounded operators on Hilbert space? say a separable Hilbert space.
I understand, but
Yeah,
the
or
D
say
of
the
H
dual.
is not going to be separable anymore, even if H itself is.
Right. So, for example, if we look at the dual of an space,
A dual of
and almost
transitive space. So Cabello-Sanchez has some results in this direction. I would have to check.
Okay, good.
So I am not 100%. My first reference would be Cabello-Sanchez. He has multiple papers. I suspect the answer is unknown.
Okay.
But I would have to double check.
Okay, good. And thank you so much again. Any other questions? Anyone? Any other questions? If not, let's thank the speaker one more time. And
thank you very much.
And Beata, I'll be grateful if you could share your slides with me.
Yes, I will send them to you. All the annotations I made will not show on them. But oops. How do I? This is what I wanted to do.
Good.
I am sorry. Well, thank you. I am attempting to. I will definitely email you this. Thank you very much.
Thank you, Beata. And now I ask Stefan to formally conclude the meeting.
Thank you.
Yeah, thank you again for the very nice talk.
Thank you.
Yeah, so probably we will not have a talk next week, if I understand correctly. So most likely in 2 weeks again. I will send you an email. And yeah, thank you very much and see you all.